Good morning, children. Welcome back to online classroom of Sri Gokulam Public School, Guruvayur. I am Jaypriya, your computer science faculty. See, children, in our last class, we've started our third chapter, that is Boolean logic. Okay, I hope you all studied the topics that we were covered in last class, isn't it? Okay, what are topic we covered in last class? Yes, Boolean logic, that is truth table, binary decision, Boolean variables, then truth values, tautology, fallacy, truth table, etc. Okay, then what is meant by truth table? Yes, truth table is a table that stores all the possible combinations of a variables, binary or logical variables. Okay, what is meant by tautology? If the binary decision or if a statement gives only high output or the result of a logical statement is always true, then it is called tautology. Okay, if the result of a logical statement is always false, then it is called fallacy. Clear? So today let us learn one more topic called how to evaluate the Boolean expression. How to evaluate a Boolean expression. See children, here we have one example. X plus xy equal to x. X plus xy equal to x. What is meant by xy? See, xy means x dot y. Okay. X dot y, that is x dot y, you can simply write as xy. X dot y you can simply write as xy. That is x and y. Okay, xy means x and y, that is logical multiplication. Okay, so let us start to solve this expression. Here how many variables? X and y, only two variables. Then we can first draw a truth table for x and y. Then write all the possible combinations for these two variables x and y. Here xy, then xy, then x plus xy. So these are the columns for the truth table. See here we can write all the possible combinations, that is 0, 0, 0, 1, 1, 0, 1, 1. It's very simple question. Okay. Then what is next step? xy. xy means x and y. That is 0 into 0. Logical multiplication. That is equal to 0. Then 0 dot 1. 0, 1 dot 0, 0 and 1 dot 1, 1. The next one, x plus xy, logical OR, x plus xy. So, 0 plus 0, 0, 0 plus 0, 0, 1 plus 0, 1 and 1 plus 1, 1. See, in Boolean logic, 1 plus 1 is equal to 1, but in binary addition, 1 plus 1 is equal to 1, 0. That is 0, 1 plus 1 is equal to 0 and carry 1. But in Boolean logic, 1 plus 1 is equal to 1. So here now let us compare x plus xy with x. Okay, let us check whether our answer is correct or not. See what are the answers we get in this column. 0, 0, 1, 1. Now let us compare with the x column. X column always shows the same numbers or same digits, that is 0, 0, 1, 1. So we can say that x plus xy is always equal to x. Clear? Okay, I will explain one more example. Listen to this question. X plus y all dash is equal to x dash y dash. Okay, that is x plus y complement is equal to x complement or y complement. Or you can say that x plus y all bar is equal to x bar y bar. Okay, all are same. See, now I write the answers for this question. So I will explain how to do this. Okay, so here x, y, x, y. Only two variables. Then you can prepare a truth table for x and y. Okay, so here first write truth table for x and y. 0, 0, 0, 1, 1, 0, 1, 1. Okay, then next one, what is next one? X plus y. Then find x plus y. That is 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1 and 1 plus 1, 1. Then find x plus y dash. So x plus y dash means the complement of these values. Complement of x plus y is x plus y dash. So here 0 complement 1, 1 complement 0, 1 complement 0 and 1 complement 0. Now what is next here? X bar, y bar. To find x bar, y bar, first you need to find x bar, then find y bar, then find x bar, y bar. So first write the column for x bar or x dash. Both are same. Then x dash means complement of x. What are the values in x? 0, 0, 1, 1. So the complement will be 1, 1, 0, 0. Okay. Then what are the values in y? 0, 1, 0, 1. Then the complement will be 1, 0, 1, 0. Okay. Then x dash, y dash, that is 1 dot 1, 1, 1, 0, 0, 0, 1, 0 and 0 dot 0, 0. Now let us check whether our answer is correct or not. Okay, you can compare this one with which one? X plus y dash. See here, what is the answer for x plus y dash? 1, 0, 0, 0. Okay, it is always equal to x dash, y dash. That is 1, 0, 0, 0. So our answer is correct. So you can work out more problems or more examples from your home. Okay, see our next topic is Boolean gates, okay, or logic gates. Okay, we already said mainly 3 types of operators: and, or, and, not. 3 types of operators, and these are the basic gates: and, or, not. Okay, that's the different types of logic gates are and, or, not, NAND, NOR, XOR and XNOR. Okay, I will explain detail. So, basic logic gates. Do you know what is a logic gate? Logic gates is an electronic circuit that works on one or more input signals to produce an output signal. Okay, logic gate is a basic electronic circuit to work on one or more input signals to produce an output signal. Okay, here we have 3 types of basic gates, that is inverter and or. Okay, see, inverter and or. Okay, inverter gate is also called NOT gate, or inverter is the another name of NOT gate. Inverter is the another name of NOT gate. Okay, so let us start with NOT gate. See, this is the logic diagram for NOT gate. Okay, this is the logic diagram for NOT gate. So when you give the input x, then you will get the output x bar. X bar means complement. That means the NOT gate always give the opposite of input signal. Okay, NOT gate always gives opposite of input. Okay, so can you see this bubble? Okay, this one, this means that complement. Okay, see, this is the truth table for NOT gate. Only 2 values here, only 1 input. See, for NOT gate will works with only 1 input and produces only 1 output. So here we have only 2 values, high and low. That is 0 and 1. Okay, 0 represent low voltage, 1 represent high voltage. Okay. Then 0 complement is 1 and 1 complement is 0. Here high complement low and low complement is high. Clear? So this is the logic diagram for NOT gate. Next one, AND gate. AND gate have 2 or more input signals and produce 1 output signal. Okay, AND gate have 2 or more input signal and produce 1 output signal. Here I am giving the logical representation for 2 input AND gate and 3 input AND gate. Okay, so this one is the 2 input AND gate. Here x, y and the output is f. This one is 3 input AND gate and the output is f. X, y, z are the input and output is f. This is the truth table for the variables x, y, z. Okay, all the combinations for the 3 values are given in the truth table. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So here When see in AND gate, any of the input is low, then the output will be low. Okay, in AND gate, any of the input is low, then output will be low. And if all the inputs are high, then output will be high. Okay, see here, in these cases, these 7 cases, one input is 0. Here 1 0 0 0 0 0 0 0. That's why all the outputs are here. All the outputs are 0. Okay, see, only one combination is 1 1 1. That's why we get only one high output. Clear? So first one, NOT gate. NOT gate is also called inverter. It works on one input and produces one output. Second one, AND gate. AND gate have 2 or more input signals and produces one output signal. Okay, in AND gate, if any of the values is 0, then output will be 0. Or any of the input is 0, then output will be 0. Then the output will be 1 only when all the inputs are 1. Or all the inputs are high, then only output will be high. Clear? The next one is OR gate. OR gate also have 2 or more input signals and produce one output signal. Okay, 2 or more input and produce one output. So this is the logic representation for or logical diagram for OR gate. Okay, here 2 input OR gate, here 3 input OR gate. Okay, one output. This is the 2 table for OR gate. Okay, here x, y, z are the combinations of x, y, z, then the output. Yeah. Okay, see, OR means logical addition. So this F means x plus bar. F is equal to x plus y, not x plus bar, x plus y. Okay, F is equal to x plus y. In AND, F is equal to x dot y. Okay, so this is x plus y. So if any of the input is high, then the output will be high. In OR gate, any of the input is high, then output will be high. So here no input is high, so the output is 0. Here 1 1, so here 1, and also all other outputs are high. Clear? So these are the basic logic gates. Clear? So children, we can derive more gates from the basic gates AND or NOR. Okay, these are the NOR, NAND, XOR and XNOR. Okay, NOR, NAND, XOR and XNOR. These are the other gates derived from basic gates. Okay, and we can start with NOR, NOR gate, NOR, NOR gate. See, NOR is just opposite of OR gate. NOR is just opposite of OR gate. See, so this is the OR gate. Okay, when the output is complemented, then we will get NOR gate. Okay, when the output of OR gate is complemented, then we get NOR gate. So this is the logical representation or logic diagram for NOR gate. You see, here you can see one bubble. Okay, this one is the representation of OR gate. Then the OR gate is bubbled. That will be a NOR gate. Okay, this is an example for 2 input NOR gate and this is 3 input NOR gate. Okay, so I said NOR is complement of OR gate. So if any of the input is high, then output will be low. Okay, that is in NOR gate the output will be high only when all the inputs are low. Clear? So this is the 2 table. Okay, 2 table for 3 variables. Okay, F means F NOR, X NOR, Y NOR, Z. Okay, so I already said in NOR the output will be the opposite of OR. Okay, in OR gate any of the input is high, then output is high. But in NOR gate the output will be high, all the inputs are low. So here only first case all the inputs are low, so we get a high output. All other cases the input is low. Okay, we can represent x plus y. See here for x and y. So for OR gate the output is xy, and for NOR gate the output is x plus y bar. Here we have 3 input x plus y plus z. Okay, OR gate x plus y plus z. Then NOR gate x plus y plus z bar. Clear? Okay. The next one, NAND gate. NAND gate is the complement of AND gate. See here, AND gate it is complemented by using NOT gate. Then we get an NAND gate. Okay, so this is the representation for NAND gate. That is AND gate with the bubble. Okay, bubble means complement. Okay, so this is the representation for 2 input NAND gate, and this is the representation for 3 input NAND gate. We already said AND gate give dot, that is logical multiplication. If x and y are the input, the AND gate give x dot y. Okay, but here x and y are the input and NAND gate give x dot y bar, the complement of AND. Okay, so this is the two table for NAND gate. See children, in NAND gate, any of the input is low, then we get the output is high. See, if any of the input is low, then output will be high. So all these example or all these combinations contains one low input, that's why the output is high, and we get a low output only when all the combinations are high. Okay, the next one, XOR. XOR is derived from OR gate. Okay, XOR is derived from OR gate. This is the logic diagram for 2 input XOR gate and 3 input XOR gate. Okay, see, this is the symbol to represent XOR. This is the N plus symbol inside a circle. This is the symbol to represent XOR. See children, for an OR gate, if any of the input is high, the output will be high. But in XOR gate, the input combinations contain an odd number of ones, then the output will be high. Okay, so this is the two table for XOR gate. Here we have 1, 1. 1 is an odd number, then output will be high. Here also 1, 1, so output high. Here 2 ones, it's an even number, so output is 0. Here 1 input, output 1. Here 2 input, output 0. Here 2 input, output 0. Here 3 inputs, so output is 1. 3 is an odd number, so output is 1. Clear? Okay. Next one is XNOR gate. Okay. See here. This is the representation for 2 input XNOR gate, and this is the representation for 3 input XNOR gate. Okay. See, in XNOR gate, when the input combination is contain even number of ones, then output will be high. Okay, when the input combinations contain even number of ones, then output will be high. So here 1, 1, it is odd 1, so output is 0. Here odd 1, output 0. Here 2 ones, 2 is an even number, so output is 1. Here output 0. Here even number of ones, output 1. Here also even number of ones, output 1. Here 3 ones, odd number of 1, so output is 0. Okay, so this is the representation and truth table for XNOR gate. Okay children, now let us wind up this section. Okay, so today we will explain or we will learn different types of logic gates and or not, NAND, NOR, XOR and XNOR, and also how to evaluate a Boolean expression. Please do more problems from your home. Okay, see you again with another topic. See children, you have to copy all the examples that I explained in this lecture video. Okay, here I am also attaching the notes that also you have to copy into a notebook and attend the text and send the answers into the given mail. Okay, then see you again with another topic. Till then, take care. Bye.